we will be talking on a class of multi-parameter car flows. So as Piyash has already talked about, just like CCR flows, car flows also is an example of an E0 semigroup. But we will not look at car flows from the perspective of E0 semigroups, but rather there is something called a product system associated to an E0 semigroup, and we will be looking at car flows on a certain class of car flows from the product system perspective. And many of the definitions you might find repetitive because Piaget has already given them, but still I'll repeat it. So we will start. First, we will be the class. So as you have seen, associated in a certain nice class of isometric representations of a semigroup, you can construct CCR flows. It is similar in an analogous way. Car flows also are also constructed from certain strongly continuous pure isometric representations. But the class we are restricting ourselves to is the class of isometric representations with commuting range projections. First, we will define that and look at a few examples, because those examples are important to us in the later part. So, and then we will look at type 1 car flows associated with isometric representations with commuting range projections, and we will see if we can characterize them fully. So first we will start with the isometric representations with commuting range projections. We will consider the semigroup under consideration for us will be closed convex cone in the d-dimensional Euclidean space Rd for d greater than or equal to 1, and we assume that the cone generates Rd and it is pointed, meaning P intersection minus P is 0. So the cone will be fixed and the Hilbert spaces we will be considering will all be separable. As Piaget has already defined them, the representation of a cone is a map from P to BH such that it satisfies the semigroup law. And it's an isometric representation. If each of the VA is isometric, it is strongly continuous. If for each xi in the Hilbert space H, the map which takes A to VA xi is continuous, and it is pure if the intersection of ranges of VA is trivial, and it is equivalent to the definition that she has given. It was a bit different. So the representations that will be talked about will all be strongly continuous, pure, and isometric, and in the latter part also they will also have commuting range projections, which is same as saying the family of projections. So these for an isometry V star, or if for each A and P we consider an isometry VA, which is given by the representation, and this is the range projection of this isometry, because the range of this projection is range of VA, and if this family is a commuting family, we call the isometric representation has commuting range projections. So all the representations we consider will be will have commuting range projections. So if P is one parametric, meaning P is the semigroup of non-negative real numbers, we define the shift operator ST for each t greater than or equal to. We define ST on L2 0 infinity by STFX. It just shifts the function by t to the left. So we define by f of x minus t if x is greater than or equal to t, or otherwise 0. So we can also consider a Hilbert space K, and we can look at ST tensor 1 on L2 0 infinity tensor K. It also has the it's also an example for an isometric representation with the commuting range projections. So as a higher dimensional analog of the shift, if we consider the cone P, we can look at its dual cone, which is defined by set of all lambda in Rd such that inner product lambda is non-negative for each A in P, and for each lambda in P star, we can define a representation S lambda of P on L2 0 infinity by S lambda A is S inner product lambda A. This index is this is the shift. This is called the pullback of the one parameter shift by this homomorphism A going to inner product lambda A, and two such representations are unitarily equivalent if and only if the norms of lambda 1 and lambda 2 are equal. So we looked at those elements in P star which have norm 1, and look at a K in N infinity, N union infinity, and take a representation, take a Hilbert space K of dimension K, and for a lambda element lambda of SP star, we look at S lambda A tensor 1 on L to 0 infinity tensor K, and we denote it by S lambda K. Take a countable, non-empty countable set I, and take a injective map lambda from I to S of P star. This is somewhat an abuse of notation, but still I'll keep it. Let K from I to N be a map. For each I in I, let Ki be a Hilbert space of dimension small ki, and the isometric representation, which is the sum of these representations S lambda I ki, that also we will denote by S lambda k. And this sum, this S lambda k, also has commuting range projections. So another important class of examples comes from a very different perspective. Look at class of all closed subsets of RD. And we define a new topology on this class of closed subsets, which is called the Feld topology or Vittori's topology. So a sequence in Vittori's topology, a sequence of closed sets AN converges to A in Feld topology if and only if lim_inf of AN and lim_inf of lim_sup of AN is equal to A, where the definition of lim_inf and lim_sup is given by this. So we look at a subset of C of RD, which is YU. It is the set of all closed subsets in RD such that minus P plus A is in A. It is closed under the addition by minus P, and they are non-empty and proper. And we consider a subset of YU, which we call XU. It is the set of all A in YU such that 0 is in A. So with respect to the subspace topology of the Feld topology inherited from C of RD, this YU becomes a locally compact Hausdorff and second countable. And there is an action of RD on YU given by take an X in A and take a X in RD and YU in A. We can look at A plus X, which belongs to YU, and XU is closed under the action of non-negative, action of P. So, and YU is the union of all XU minus all translates of A, where A is in minus P. So we define representation of P on L2 XU. So we look at XU and Radon measure YU invariant under the action of RD on YU, and we define the shift semigroup V mu. L2 XU mu associated to mu by VA mu is shifting by A. This is similar to the shift that we have earlier defined on 0 infinity. You can look at YU as real numbers and XU as the non-negative real numbers. Then this is very similar to that. So now we will come to the car flow part of the talk. We'll look at type 1 car flows associated to isometric representations with commuting range projections. So first we'll define a product system. As I said, product systems can be associated to E0 semigroups, and in the case we are considering this association is bijective for closed convex cones. So it's a nice kind of association, meaning that two E0 semigroups are cocycle conjugate if and only if the corresponding product systems are isomorphic. So a product system is a field of Hilbert spaces, just like vector bundles. This is like a bundle of Hilbert spaces. For each A in P, you have a Hilbert space E of A. And they have a measurable structure over them, which I won't elaborate on. And on the fibers, you have a multiplicative rule, xi tensor eta going to xi eta. That multiplication has to satisfy certain compatibility conditions with the measurable structure of E, which also I won't elaborate further. So as she mentioned, CCR flows are defined on certain symmetric Fock spaces, but here we have the antisymmetric analog of the same thing. So given I will define the antisymmetric Fock space associated to a Hilbert space. Given a non-zero Hilbert space H and permutation on n symbols, you can define a unitary U sigma on the elementary n tensors by permuting the elementary n tensors, and this can be extended to a unitary on H tensor n. The space of antisymmetric n tensors is defined by set of all those xi in H tensor n such that U sigma xi is sign of sigma xi for each sigma in Sn. And we conventionally set HA tensor 0 to be C. And the antisymmetric Fock space is the direct sum of all those antisymmetric n tensors for each n. And you can suppose you have two tensors, two elements in H tensor n. You can take their alters. This is the projection of xi onto the antisymmetric n-dimensional antisymmetric space, and then also suppose you have xi in H tensor n and eta in H tensor m. You can take their wedge product to get a element in HA tensor m plus n. So now we are ready to define product system of this CAR flow associated to V. Just like CCR means canonical commutativity relation, here it means canonical anti-commutativity relation, which I forgot to mention. So suppose V is an isometric representation of P on H, and we consider this field of Hilbert spaces, gamma A kernel VA star. This is the antisymmetric Fock space associated to kernel VA star along with the product rule. So you take eta xi in gamma A kernel VA star and eta in gamma A kernel VB star. This should be VB star. Then you get VA eta wedge xi in gamma A of kernel VA plus B star. So this is called the product system of the car flow associated with V. And and the thing is that if so this we denote by EV. So for two isometric representation V and W of P, EV is isomorphic to EW if and only if V and W are unitarily equivalent. So a product system is called a subsystem of a given product system if the fibers of the smaller subsystem product system is contained in the larger. So a section is just, as you might be knowing, it's a map from P to E such that UA is in EA, and it's called a unit if the section is multiplicative. And we denote the section of set of units by UE for a product system E. So the product system may not have any units. If it is it has some units, it's called spatial, and car flows are always spatial because there is vacuum unit which is 1 plus 0 0 0 for each A. And if the so we call a product system type 1 if the only subsystem containing all the units is E, which is in some sense saying that units generate the product system. So there is a it's also true in the case of CCR flows. There is something called additive cocycles, which are in one-to-one correspondence with the units. So there is this class of additive cocycles, and there is class of units, and there is a bijective correspondence between them. So an additive cocycle is a map from P to H, which satisfies these conditions. Xi A belongs to kernel VA star for each A in P, and Xi A plus B is Xi A plus VA Xi B for each A in P. So if you can remember, for the S lambda, the pullback of one parameter shift, the characteristic function of 0 lambda A for each A in P, this is a unit. And for the V mu that we have constructed, the characteristic function of XU minus XU plus A for each A in P is an example. And we will see that up to scalars, these are the only examples. So unit is exponential if you look at the vacuum unit and take inner product with it. If the inner product is 1, then the unit is called exponential. So there is in the one parameter case, there is a bijection between exponential units and additive cocycles, and that map we call it log. But for a general cone, this log is only an injective map. It's not bijective. But still, given a unit, you will have a additive cocycle associated to it. So just like the CCR case, there is something called there in the one parameter case, CCR flows and car flows are actually equal. So in the multi-parameter case, it's not so. So like in the CCR case, we can define an exponential map, but it's in some sense certainly is in some sense artificial, because you look at the one parameter semigroup TA, TA for t greater than or equal to a and a in p, and look at exponential vectors there. Because it's isomorphic to CCR flow, you can construct exponential vectors there and put them all together and get call it exponential of xi, and you can look at exponential of log u for each any unit u, and in general exponential of xi is not a unit for EV, but all units are of this form, are of exponential of log u. So it's every unit is exponential, but not every exponent is a unit. So the question we will be considering, suppose you are given an isometric representation of P with commuting range projections. So when is the corresponding product system of the car flow type 1? When is it generated by units, or when does it have enough units to generate the product system? It turns out that, so suppose you are looking at a single additive cocycle and look at the smallest reducing subspace of V containing xi A, then we can construct a non-zero invariant radon measure on YU such that V restricted to xi is V mu, and exponential xi is a unit if and only if V mu is unitarily equivalent to S lambda. So given if you look at a subspace generated by this additive cocycle, it's always type 1. So after a Zon's lemma argument, what we get is that any type 1 product system is actually a sum of these S lambdas. So take a map lambda, which is injective from I to S of P star, and a map K from I to N infinity. We denote the product system of the car flow associated to S lambda K by E lambda K, and a product system EV of car flow associated to V is type 1 if and only V is S lambda K associated to these maps lambda and K. And because isometric representations and product systems are in one-to-one correspondence, E is isomorphic to E lambda K. So as Piyasha had mentioned about index, we can also make a comment on the index of E lambda K. So E lambda K is associated to S lambda K. So and the index of this product system or the corresponding CR flow is actually additive. It is the sum of index of E lambda IKI which are associated to S lambda IKI. And also we can, the gauge group of CR flow is its group of automorphisms. So we can also make because of this conclusion, because of the earlier conclusion, we can also make a comment on the gauge group also. It's the group of automorphisms of the product system, but I won't elaborate on this. And I will stop with this conclusion. Stop with this.